Let's work a linearization example. The example that we're going to take today is going to be an aircraft in straight and level flight, and we want to monitor the longitudinal dynamics, that is basically the velocity of the aircraft as it travels through the air. So we're going to take a quick drawing of an aircraft here, and to that aircraft we're going to add some sort of thrust force that keeps it moving and some sort of drag force as it goes through the air. And we're not going to worry about the vertical dynamics or the pitch or yaw or any of the other states. What we're interested in right now is just the velocity. So I'm going to take a second and I'm going to write the equations of motion for this aircraft, expressing the velocity dynamics as v, the acceleration as v dot, so as opposed to x double dot. Since we're only interested in the velocity, we don't actually care what its position is in the air. So I'll write that equation now. Hopefully at this point you're starting to get comfortable with writing your free body diagrams and then going rather quickly to your equations of motion. So now we have the expression that describes this in terms of the forces, but we don't know what exactly these forces are. The thrust force we'll assume is the input to the differential equation. So Ft is just going to remain Ft for now. On the other hand, the drag force is dependent on the air properties and the speed that the aircraft is moving, and we can substitute that into the equation. And so I will take this and write that equation now. You may recall this equation from other classes. It's 1/2 rho, which is the density of air, times CD, which is a drag force, or a drag coefficient on the aircraft. It has to do with the shape and how smooth it is. A is the frontal area exposed to the oncoming air, and V is the velocity of the aircraft itself. So we can see that this equation is clearly nonlinear because we have this term right here. So we need to do a linearization process to end up with something that expresses the velocity of the aircraft in a linear way. We know that because the nonlinear term is the v squared, that we're going to start by writing a Taylor series expansion for the v squared and then substitute it in. So let's work on the Taylor series expansion first. At this point, I'd like you to stop the video and write the Taylor series expansion for v squared yourself, and then restart it when you're ready to check your answer. Okay, hopefully you've got the Taylor series expansion written at this point. I'll go ahead and write it here so that you can check your work. So what I've written here now is an expression for v squared, an approximation in the vicinity of v naught, which is going to be our steady state operating point. So what we have here is the Taylor series expansion. We evaluate the function, the nonlinear function itself, at the operating point, so that gives us the term v naught squared. Then we evaluate the first derivative of the function, again at the operating point. That gives us the 2v naught. And then we multiply that first derivative by the distance that we are from our operating point. And so we take v minus v naught, which is basically the actual operating point minus the steady state operating point that we're linearizing about. It's convenient if we rearrange this equation to eliminate the multiplication of the term in parentheses and wind up with only two terms. So I'm going to do that now. This simplified expression will help us. And so now we can substitute this back into the original nonlinear differential equation and see what we come up with. Great, now we have a linear differential equation. You can see that because we only have v and v dot in the equation, as well as some constant terms. Ft is our input to the system. And now we have this extra term that involves the v naught squared term. which is fine. The squared doesn't affect us because that's not one of our variables of interest. V naught squared is just a constant. But we now have a bunch of terms in the expression that we don't really need because what we're interested in is how much we're operating above or below V naught. And so what we're going to do is we're going to expand this expression in terms of some new variables. Pause your video now and try to determine what these new variables should be. These expressions are arbitrary, and they are just expansions of ft and v to say that as opposed to them just being a variable that goes from negative infinity to infinity, we now have an ft naught that's offsetting it. So we can still achieve all values between negative infinity and infinity just by altering the value of ft hat, but now we're offset by a value of ft naught, which is our thrust that keeps us moving at a constant speed at our operating point. Similarly, we've written v as v naught plus v hat. And again, this is an arbitrary transformation. We're just basically shifting v hat up by a value of v naught and saying that that whole expression is going to be equal to any value of v. And realistically, we're doing this all the time anyway. The difference is that we're saying that our point about which we're measuring ft and v is 0. And so what we're really doing is just shifting up to some other arbitrary values that happen to be the equilibrium values for our aircraft. So now I'm going to go ahead and I'm going to substitute these two expressions into the differential equation so that we now have the differential equation in terms of the steady operating values as well as the changes away from those steady operating values. So let me go ahead and do that. This expression is a little bit of a mess, so let's do a few simplifications. The first one is that we're going to note that v naught is a constant. And so on the left-hand side of the equation where we have m d dt of the quantity v naught plus v hat, we know that the derivative of v naught is going to be 0. And therefore, really the left-hand side is just m d dt, the derivative of v hat, which is the variable that's going to be changing. So that's one simplification. And then on the right-hand side of the expression, I'm just going to do a little bit of algebra to eliminate some of the products and distribute the v naught inside the brackets. So now we've simplified this expression, but we still have a bunch of terms hanging around that we want to see if we can still simplify even more. So what we're going to do is shift the last term on the right-hand side, the 2v naught times v hat, over to the left-hand side. So we basically have a standard form of a differential equation. We'll have the m times the derivative of v hat plus some constants times v hat itself. And then on the right-hand side, we'll have effectively what's the forcing function of the differential equation, which will be a bunch of terms, some of which will be constant, some of which will be time varying. So let me do that algebra now. At this point, we've actually got a pretty good differential equation. It's first order, as you can see on the left-hand side, in terms of the new variable, v hat, which expresses the distance or the velocity difference between the original operating point, v naught, and the actual speed that the aircraft is traveling at any instant in time. On the right-hand side, we still have a couple of extra constants. The ft naught value is constant, and the 1/2 rho a cd v naught squared value is also constant. There's a hidden relationship between these if we're taking that velocity to be at some equilibrium point, and we're defining these variables from some point where the aircraft is truly in equilibrium. And we find that by going back to the original nonlinear differential equation and writing it at that equilibrium state. So let me do that now. notice that this is just the original differential equation, but now I've written in that we have ft naught at this particular operating point, and we're traveling at a velocity v naught, all right? And so by definition, I'm saying that ft naught is the thrust that keeps us at the constant operating point v naught. If that's the case, we're at equilibrium, and that means that v naught is 0, and the left-hand side of this equation is 0. And therefore, we have this relationship between ft naught and v naught. We can then take these and we can substitute this relationship into the differential equation, and we'll start to see some cancellation on the right-hand side of the equation, and therefore the expression will get simpler. I'll do that now. Since this was at equilibrium, all I did is basically say that the quantity ft naught minus 1/2 rho a cd v naught squared was equal to 0. Both of those terms appeared in the expression, and so their sum was 0, and therefore they dropped out. And what we're left with now is m d dt v hat plus rho a cd v naught times v hat. And that's equal to ft hat, which is the variation in thrust, which causes the change in the amount of velocity above or below our operating point v naught. So now we actually have an expression that represents the incremental change in velocity as a result in an incremental change in thrust. Note that the substitution that I made is only valid if you have truly defined your input variable, in this case ft naught, to be the value of that input that holds the system at equilibrium. So the relationship that I wrote in the line above here is not true in general, but it does explain the relationship between those two variables that I defined, and therefore it's valid to cancel those two out of the equation since they are representing those equilibrium terms. So that's it. We now have the equation that we were looking for. It describes, we're back to a first order linear differential equation. It turns out it has almost exactly the same form as the original differential equation, with the exception that we actually ended up losing a factor of 1/2 in the process. That would have been sort of right there in the equation. And we've rewritten in terms of these perturbation variables about the operating point. So that's all there is to it. Generally, you follow the exact same procedure. You're going to get rid of the nonlinear term using the Taylor series expansion. At that point, you do have a linear expression. You just have a bunch of constant terms hanging around. And that's perfectly fine. You can use that equation. But if you're looking to do some sort of control, or you just want to know about the incremental change, then we define this equilibrium operating point. We substitute it in and eliminate a number of variables. And you'll see the same pattern emerge basically each time that you do a linearization like this. You'll find some static terms that will cancel out, and you'll be left with a much cleaner expression for the variations. So that's it for that example. Check your work, make sure that you've got a pretty good handle on this, and that's it.